All right, welcome back. This is going to be the 8th video here in our S1 equation series. In this video, we're going to introduce a concept called split markers. Split markers occurs when S1 does not equal rotation speed. Now, the purpose of this video is to answer this question. When S1 does not equal rotation speed, meaning we have split markers, why do we use critical field length and not takeoff ground run to determine our distance to reference zero? Well, first we want to know reference zero because, per our rules, reference zero must occur no later than the departure into the runway. Now, in our takeoff planning, in general, we are pretty conservative, and we plan for worst-case scenario being an engine failure. During your time here in pilot training, you'll hear a wide variety of takeoff briefs, and hopefully most of them state the obvious fact that if an engine failure occurs prior to S1, you are going to abort. So, when S1 equals rotation speed, the only times I would ever take an engine failure into the air would be if it occurred at or above my rotation speed. So again, S1 equals rotation speed. The only times, let me change my color here. The only times I would ever take an engine failure into the air in this scenario would be if it occurred at or above my rotation speed. And that's because in this scenario, S1 equals rotation speed. At rotation speed, we're committed to the takeoff. We cannot abort. So no matter what the malfunction is or emergency is, we're taking the aircraft airborne. In which case, if this happens, I calculate my distance to reference zero as my takeoff ground run plus my takeoff flare distance. And that incorporates the fact that I've accelerated on two good engines to my rotation point, and that being takeoff ground run, lose an engine at rotation speed and take it into the air. The distance to reach 50 feet now is my takeoff flare distance. Takeoff flare distance incorporates the idea that we have lost one engine. So why then do we use critical field length and not takeoff ground run? Well, if we run into the scenario of S1 not being equal to rotation speed, so maybe S1 equals either refusal or max braking speed. For this scenario, we'll just say S1 equals refusal speed. We now have a weird scenario on our hands. We're committed to the takeoff at refusal speed, but there's now a point on the runway in which we're committed to the takeoff, but we're not yet airborne. So let me ask you this question. If I lost an engine at or above refusal speed, but before rotation speed, if I lost an engine here, could you tell me when am I going to rotate? Great grammar right there. When am I going to rotate? And can you answer me this question? When will I reach reference zero? Why do I need to know that? Because reference zero must occur no later than the departure and per our rules. So, do we have a set data, or do we have a set speed that defines if we lose an engine where we're going to rotate? Yep, you probably noticed it down here at the bottom, critical engine failure speed. So if I lose an engine at critical engine failure speed, decide to continue and accelerate to rotation speed, that distance is going to be critical field length. So when S1 does not equal rotation speed, I'm using critical field length plus my takeoff flare distance to determine reference zero. There we go, equals reference zero. Sorry, that looks a little sloppy. Critical field length plus takeoff flare distance equals reference zero when S1 does not equal rotation speed. Now why, when we have split markers here, do we use this calculation of reference zero? Well, when we have split markers, there's now a time on the runway in which we're committed to the takeoff but not yet airborne. So if I lose an engine during that time frame, I want to know where I'm going to rotate. It makes sense to me that if I lost an engine prior to rotation speed, so before rotation speed, if I lost an engine, I'm going to rotate after that original point being takeoff ground run. And I need to know where I'm going to rotate. The only set data that we have that gives us a defined distance of when we're going to rotate if we lose an engine is critical engine failure speed and critical field length. So it makes sense that if I lose an engine after refusal speed, I'm going to rotate somewhere over here. I don't know the exact point, but if I plan ahead of time for the runway required to be critical field length plus takeoff flare distance, I take into account this point on the runway in the second scenario, in which case, or I take into account if I lose an engine after refusal speed, I'm committed to the takeoff and not yet a rotation speed. So by using critical field length and not takeoff ground run, to calculate reference zero. I have all my bases covered, and I now know where I'm going to reach reference zero, or at least I know a general distance, and I know that I'm not going to, or I can plan ahead of time how much runway I'm going to need for my takeoff in the event of split markers. All right, now that we've determined that to calculate reference zero when we have split markers, we need to use critical field length instead of takeoff ground run, we're now going to introduce the takeoff acceleration check, which is required when we have split markers. So what is the takeoff acceleration check? Simply put, it is a test to determine whether or not our engines are performing at the expected rate we are anticipating. So the takeoff acceleration check, when we choose a speed to set that test at, must occur at least 10 knots prior than whatever we determine to be our S1. And that, the reason for that is because if, let's say we do the takeoff acceleration check and we determine at that speed our engines are not performing what we need them to do, or they're just, maybe there's a malfunction going on, we need a little bit of buffer to actually make a decision to abort and bring the aircraft to a stop. And using that 10 knots or greater or prior to S1, that gives us a little bit of time to make the decision to abort and not exceed any parameters or exceed S1. Now normally, when we choose our takeoff acceleration check speed, we're just going to choose our 80 knot call. Now why is that? Well, we don't want to add any unnecessary calls or any excessive calls during the takeoff procedure, being a critical phase of flight, so we just want to make it as simple as possible. So at 80 knots, we'll use that as our takeoff acceleration check, and we need to determine what distance we're going to see at 80 knots to make sure our engines are producing the correct amount of thrust. So let me change colors here. Red. If you go to page A3-55, down here at the bottom in your performance manual, or page P32 in your handheld checklist, you'll find the takeoff acceleration check table. Now let's read the instructions at the top. Number one, liftoff speed is going to be our rotation speed plus 3 knots. All right, number two says takeoff ground roll must be computed with unfactored wind conditions for accurate acceleration check. For our purposes, we don't take into account the wind, so you can leave number two to the side and just worry about number one. So let's say today our rotation speed is 114 knots. That means our liftoff speed is going to be 117. So let's go down here to the bottom for our liftoff speed portion of the graph. We have, let me see, 119, 118, 117 here. Yep, that's 117. Now we're going to go up a certain distance. For this example, we don't have any set data, but let's just say our takeoff ground roll today is about 3,100 feet. Again, no set amount of days, just an arbitrary one to work out this problem. So we take from 3,100 feet, there we go, straight line, and meet us at 117. I'm not quite done yet, but we have that point. Now, as best I can, I'm going to go back on the graph at the same rate here until I reach my 80 knot speed. There we go. And now, there we go, great straight line. I'm going to go left here to my distance side, another straight line, and determine what that is. That looks to be about 1,200 feet or so. So I have now determined what distance I should see for my takeoff acceleration check. Let me go back here. So that's 1,200. So at 80 knots, I should see 1,200 feet, or I should be 1,200 feet down the runway. Now, in practicality, we're not going to see an exact distance as that, because when we're on runways, we just see 1,000 board. So say, for example, we're on the 12,000 foot runway at Columbus. We would see the 11 board and then the 10 board. I should be just past the 10 board somewhere and approaching the 10 board, or yeah, I should be just past the 11 board and approaching the 10 board on my takeoff ground run. There's our T1 when I perform my acceleration check at 80 knots. And there you have it. In the next video, we're going to discuss an actual example of split markers and how we would run all the data associated with it.